Okay, I've always wanted to learn paleontology, so I literally just Googled paleontology textbook, and this is one of the first things that came up. I'm turning off this fan, maybe just put it on low. So we're just going to read this textbook. I'm having a little problem here, a little problem there. And we're going to start with the table of contents and just decide which chapter to start on. We've got paleontology as a science. I don't know if I want to really go through that chapter. It's just kind of describing what paleontology is. I kind of know what it is. It's the study of fossils and artifacts predating history. History meaning the written word explaining humanity and the world. This predates all that. And I think it also predates archaeology, which is the study of human artifacts. So I think we're going to start with fossils in time and space. So that's what? Page 22. So let's just scroll down. Can we skip up to pages? I don't know how to use this fucking shit, man. Alright, we're just gonna scroll. We're just gonna scroll through all this shit. These are some pretty cool photos though. Now I'm kind of getting FOMO of the first chapter. Maybe if we think we need to, we'll go back and look at the first chapter. But here we go. Chapter 2, Fossils in Time and Space. Are we gonna read these key points? Do we give a shit? I mean, we're going to read about all this shit in the chapter. So I think we're just going to skip ahead. All right, and I'm just going to read this shit out loud. And hopefully I don't get a copyright violation. So, the Earth is immensely old, and the distribution of continents and oceans has changed radically over time. Okay, so that would be referring to continental drift, Pangea and such. Early paleontologists did not know these things, and so they tried to pack the whole of the history of life into a relatively short span of time, visualizing trilobites of I thought it was I thought the word trilobites was going to mean like a quantity or something. No. Visualizing trilobites or dinosaurs inhabiting a world that was much as it is today. Life on Earth, however, has been evolving for up to 4 billion years, and there has been a complex story of fossil groups coming and going and continents moving from place to place. Okay, so paleontologists used to think that the Earth was exactly the way it is today for as long as it's existed, and that led them to believe that life fit into a shorter time frame. So life on Earth, however, has been evolving for up to 4 billion years, and there has been a complex story of fossil groups coming and going and continents moving from place to place. How do we develop geographic and temporal frameworks that are accurate and reliable enough to chart the distributions of fossil organisms through time and space? Okay. Geographic meaning throughout the locations of the world, and temporal, I don't know what temporal means here. Temporal. I don't know. Fortunately, paleogeographers and stratigraphers, I don't know what that means. The fuck is a stratigrapher? Like stratosphere? I doubt it. Maybe they examine different layers of rock. That's my guess. Are now equipped with a range of high-tech methods, virtually all computer-based, that provide a greater consensus for models describing the distributions of the continents, oceans, and their biotas throughout geological time. I believe biotas here means the plural for biome. So, for instance, from what I've heard, Antarctica used to be a different biome. It used to be a tropical rainforest. That kind of shit. Fossils also store information on the finite strain and thermal maturation of rocks located in the planet's mountain belts. Okay. All right, so they look at the layers of rocks and the heat signatures of them and how they've matured over time. Okay, and the strain on those rocks, so like how those rocks have been impacted. Located in the planet's mountain belts, allowing the tectonic history of these ranges to be reconstructed. Thermal maturation information is important in identifying the levels of thermal maturity of rocks and the gas and oil windows in hydrocarbon exploration. So I'm guessing they're just using high-tech shit to look through these rocks and try to figure out how old they are by looking at how hot they've been in the past. I'm guessing they're using technology to like see how hot these rocks might have been in the past, and there's probably certain signatures that they can pick up with that technology to determine that. And finite strain is just what has happened to these rocks. What kind of events have affected the physical but the physical texture of these rocks and such. Thermal maturation information is important in identifying the levels of thermal maturity of rocks. All right, I already read that. In some cases, fossil shells also contain isotopes and other geochemical information that can identify changes in global climate. So I'm pretty sure isotope, that is a term from chemistry. I remember hearing that in chemistry class. And it does say geochemical information. So I'm guessing they're looking at very small chemical signatures within these rocks to try to age them, to try to date them. Here's a quote. Frameworks. 6 distinct aspects of Tuscany. We therefore recognize 2 when it was fluid, 2 when level and dry, 2 when it was broken. And I prove this fact concerning Tuscany by inference from many places examined by me. So do I affirm it with reference to the entire earth from the descriptions of different places contributed by different writers. From 1669, how the fuck was this guy determining that there were different times when Tuscany was fluid, level and dry, and broken? How the fuck did he figure that out in 1669? I have no fucking clue. Nicholas Steno, the prodromus of Nicolaus, probably, Steno's dissertation concerning a solid body enclosed by process of nature within a solid. No fucking clue what's going on there, except that he knows some shit, and I don't know how he knows it. Before the distributions of fossils in time and space can be described, analyzed, and interpreted, fossil animals and plants must be described in their stratigraphic context. All right, I think we're going to find out what stratigraphy means. A rock stratigraphy is the essential framework that geologists and particularly paleontologists use to accurately locate fossil collections in both temporal and spatial frameworks. Accurately locate fossil collections in both temporal and spatial frameworks. So they're trying to, I'm guessing temporal means temperature. But I could be wrong. And spatial frameworks. So they're trying to figure out how hot these fossils might have been throughout time and where they might have been located. It seems not surprisingly that like a fine bottle of Italian wine, this can be traced back to the sunny pastel landscapes of Tuscany and the Renaissance. So it's going to talk about Leonardo da Vinci, it seems. The origin of modern stratigraphy can be traced back to Leonardo da Vinci and his drawings. Pioneer work by the Danish polymath Nicolaus Steno, or Niels Stensen. This motherfucker got 2 names? In northern Italy, during the late 17th century, established the simple fact that older rocks are overlain by younger rocks if the sequence has not been inverted. Why would it be inverted? That's figure 2.1a. Where's figure 2.1a? Right here? Is this 2.1a. This is A. So this is what that's referencing. I don't know what's going on here, man. What the hell? It's gonna describe it right here. Steno's series of diagrams illustrating the deposition of strata, their erosion and subsequent collapse. 25, 24, and 23. So this is 25, 24, 23. So this is deposition of strata, their erosion and subsequent collapse. So I'm guessing this is the deposition. I don't know. I like it. It gets placed in a different layer, but it looks like, yeah, it moves in some way. And you got this shit at the top. I don't know what's going on here. And then erosion. Would this be erosion? So they all come together by erosion by water? Don't really know. Let's go back to the main text right here. So, Nicolaus Steno, I hope I'm pronouncing that right, his law of superposition of strata is fundamental to all stratigraphic studies. In addition, I don't really know what strata means. In addition, Steno established in experiments that sediments are deposited horizontally and rock units can be traced laterally, often for considerable distances. Remarkably simple concepts to us now, but earth-shattering at the time. But what has this got to do with Da Vinci? Okay, so it's like rocks get distributed horizontally first, maybe, and then they erode. Then they get settled within the Earth's surface, and then they erode and become solid with all the other rocks, maybe? Don't know. Leonardo da Vinci is famous for many things, and his contributions to science are refreshingly modern when we look back at them. In his art, Da Vinci essentially rediscovered geological perspective some 200 years before Steno during the Renaissance. In his drawing of the hills of Tuscany, Da Vinci portrayed a clear sequence of laterally continuous horizontal strata. Okay, so I'm guessing, yeah, that's what this means, is like when you have geological surface, when you go horizontal, you have the same age of rocks. But when you go vertical, it gets older and older. I'm guessing that's sort of what this is talking about. So you get older and older as you go deeper, but not as you go horizontal, which makes sense because of gravity and erosion, etc. In his drawing of the hills of Tuscany, Da Vinci portrayed a clear sequence of laterally continuous horizontal strata displaying the concept of superposition. Moreover, I'm guessing superposition, I learned about the term superposition in quantum physics when I was studying that. It's essentially, in quantum physics, when an electron, I think it's specifically an electron, but it could be other subatomic particles, they can be essentially two things at once. Very different from how we see the physical world. An electron can be like both two colors at the same time, or it can be positive or negative at the same time, but electrons are always negative. I'm not very knowledgeable about quantum physics. Anyway, moreover, about a century after Steno, Giovanni Arduino recognized, again using superposition, three basically different rocks suites in the Italian part of the Alpine belt. A crystalline basement of older rocks deformed during the late Paleozoic Variscan orogeny, don't know what the fuck that means, was overlain comfortably by mainly Mesozoic limestones deformed later during the Alpine orogeny. These in turn were overlain unconformably by poorly consolidated clastic rocks. I don't really know what any of these ages are, or these orogenies. I'm guessing it's just periods of time, you know. But it's just saying like one layer of rocks from one period of time overlain by another layer of rocks from an earlier period of time, so it took place later. No, not earlier, sorry. One layer of rocks that's older, laid over top is a layer of rocks that's younger, and then younger and younger and younger. So later and later and later. Oh, goodness. These in turn were overlain unconformably by poorly consolidated clastic rocks, mainly conglomerates. So they're younger, so they're not as eroded, they're not as together. These three units constituted his primary, secondary, and tertiary systems. The last term has been retained and formalized for the period of geological time succeeding the Cretaceous. I guess the Cretaceous period. Are we going to look at these diagrams? Do you want to look at these diagrams? I guess we'll look at them. So we have primary, the base, and then you have secondary. These are all different layers of rock. I don't know why the fuck this is brick right here. I don't know. But it's all, as you go farther down, the rock becomes more solid, it seems. More consolidated. These three divisions were used, so this is, figure 2.1b. So what we were just reading, that's this. This is the visualization for that. These three divisions were used widely to describe rock successions elsewhere in Europe, showing the same patterns, but these three systems were not necessarily the time correlatives of the type succession in the Apennines. So I guess what it's saying is different areas have different rock structures, which makes sense. There is now a range of different types of stratigraphies based on, for example, lithology or lithostratigraphy. Don't know what that is. Fossils, biostratigraphy. Oh, okay. So stratigraphy of whatever the fuck lithology means. Don't know what lithology is. Maybe lithium? Maybe they're dating things using lithium, the element? Don't know. Maybe there's a lot of that in the earth. I know that it is used for batteries. That's all I know. So there's also a stratigraphy based on fossils, which is biostratigraphy. Tectonic units, such as thrust sheets. Tectonostratigraphy. That makes sense. Tectonic plates, the plates that shift and cause continental drift. So they're dating those or examining the layers of those. And then magnetic polarity. Magnetostratigraphy. So they're examining layers of magnets and the Earth's magnetic field to determine the age of the Earth and such. Chemical compositions, chemostratigraphy. That makes sense, examining layers of chemicals, I guess. Discontinuities, allostratigraphy. Okay, so they're measuring how things are different across different layers and different parts of the Earth. Seismic data, I don't know how that's different from tectonic plates and tectonic units. I guess like the tectonic units moving, measuring how earthquakes affect the layers of the Earth. And depositional trends, cyclo and sequence stratigraphies. So how rocks have been displaced and deposited, how they've been deposited in the Earth's crust. The first two have most application in paleontological studies, although sequence and cyclostratigraphic frameworks are now providing greater insights into the climatic and environmental settings of fossil assemblages. So the first two, let's break that down. The first two have most application in paleontological studies. So the first two are lithology, lithostratigraphy, don't really know what that means, and then fossils, biostratigraphy. That makes sense. The deposition of fossils being deposited in the Earth's crust. So the first two have most application in paleontological studies. That's what we just tried to figure out. Although sequence and cyclostratigraphic frameworks are now providing greater insights into the climatic and environmental settings of fossil assemblages. So what is cyclostratigraphic? Didn't it just say, Yes, cyclo and sequence stratigraphies. So depositional trends and analyzing how things have been deposited into the Earth's crust. So that kind of science is now providing greater insights into the climatic and environmental settings of fossil assemblages. So it's helping us figure out how hot things were back in the day, how the Earth's climate has changed over time, and environmental settings. So what the environment was like what the weather was like. I guess that's part of climate. So environmental settings of fossil assemblages, I guess maybe what types of animals existed at which times and where they existed, don't know. Here, however, we concentrate on lithostratigraphy, rock framework, biostratigraphy. Oh, okay, so it explains rock framework. So how rocks, what kind of rocks? So maybe lithostratigraphy is analyzing the types of rocks and their frameworks, how they're composed. Maybe that's what lithostratigraphy is. And then biostratigraphy, ranges of fossils, and chronostratigraphy, time dimension, trying to date these fossils and these rocks. Okay, so now it's going to go in depth on lithostratigraphy. So now we're going to actually figure it out. All aspects of stratigraphy start from the rocks themselves. Their order, this is probably more boring than you all were expecting, but this is science, bitch. This is fucking science. This is how it works. Science is boring until it's cool. You know, you got to have the boring before you get to the cool. So all aspects of stratigraphy start from the rocks themselves. Their order and succession, or lithostratigraphy, are the building blocks for any study of biological and geological change throughout time. So studying the rocks, studying the order of the rocks, I guess not the structure of the rocks, it doesn't say that. So basic stratigraphic data are first assembled and mapped through the definition of a lithostratigraphic scheme. What the hell does that mean? I'm going to read that again. Basic stratigraphic data are first assembled and mapped through the definition of a lithostratigraphic scheme at a local and regional level. Okay, so they look at the rocks first. They look at the order of rocks first before they start examining fossils, chemicals, any of those other stratigraphic types, I guess. The formation, a rock unit that can be mapped and recognized across country. Sorry, I'm starting to like lose focus here a little bit, but I'm locking back in. The formation, a rock unit that can be mapped and recognized across country, irrespective of thickness, is the basic lithostratigraphic category. Okay, so the formation of rocks that spread across the crust, across the country. Cool. A formation may comprise one or several related lithologies, different from units above and below. All right, so that's consistent with what we've been reading, and usually given a local geographic term. So I guess different formations of rocks have different terms and different names. A member is a more local lithologic or lithologic development, usually part of a formation, whereas a succession of contiguous formations with some common characteristics is often defined as a group. All right. Okay. Groups. So this is just categorizing different formations, different clusters of rocks, it seems. Groups themselves may comprise a supergroup. All stratigraphic units must be defined at a reference or type section in a specified area. So you got to say which kind of rocks these are. Got to know. Unfortunately, the entire thickness, getting texts, 1 second. A member is a more local lithologic development. All right, we already read that. All stratigraphic units must be defined at a reference or type section in a specified area. Unfortunately, the entire thickness of many lithostratigraphic units is rarely exposed Instead of defining the whole formation, the bases of units are defined routinely in basal stratotype sections at a type locality. Instead of defining the whole formation, the bases of units are defined routinely in basal stratotype sections at a type locality, and the entire succession is then pieced together later. I don't know what the fuck is going on here. I'm going to read that one more time. Unfortunately, the entire thickness of many lithostratigraphic units is rarely exposed instead of defining the whole formation. The bases of units are defined routinely in basal stratotype sections at a type locality, and the entire succession is then pieced together later. Okay, so the methods don't get the whole picture. They get pieces, and you got to piece them together later. Okay. These sections, like yardsticks or the holotypes of fossils, act as the definitive section for the respective stratigraphic units. Okay, so they help identify and classify different units of examining layers of rocks. These are defined within a rock succession at a specific horizon, where there is a lithologic boundary between the two units. The precise boundary is marked on a stratigraphic log. Since the base of the succeeding unit defines the top of the underlying unit, only basal stratotypes need ever be defined. So you're defining the stratotypes by looking at the bottoms of each of them to see how they separate. And the stratotypes being the different sections of rock. A stratigraphy, illustrated on a map and in measured sections, is required to monitor biological and geological changes through time, and thus underpins the whole basis of Earth history. Okay, so this is some important shit here. This is how we understand the Earth's history. It is a simple but effective procedure. Successions of rock are often divided by gaps or unconformities. These surfaces separate an older part of the succession that may have been folded and uplifted before the younger part was deposited. Okay. Commonly, there is a marked difference between the attitudes of the older and younger parts of the succession, but sometimes both parts appear conformable, and only after investigation of their fossil content it is clear that the surface represents a large gap in time. So they're looking for gaps in the rocks to determine how the age difference between the different layers. And sometimes you don't have as many unconformities or gaps, so you have to analyze the fossil record. And maybe that involves carbon dating a little bit, I don't know. Early geologists thought the Earth was very young, but the Scottish scientists James Hutton, 1726 to 97, noted the great cyclic process of mountain uplift followed by erosion, sediment transport by rivers, deposition in the sea, and then uplift again, and argued that such processes had been going on all through Earth's history. So he was looking at mountains erupting from probably continental drift, and then those upliftings cause erosion of rock. I don't know how, maybe through rivers or rain, and then that deposits sediment residue, that is probably a product of the uplifting of the Earth's crust. Sediment gets transported, yes, by rivers, and then it gets deposited into the sea, and then it settles, and then it uplifts again. Okay. He wrote in his Theory of the Earth, 1795, that his understanding of geological time gave no vestige of a beginning, no prospect of an end. interesting. So he can't see a beginning and he can't see a prospect of an end to these processes. An example of Hutton's evidence is the spectacular unconformity at Sicar Point, Berwickshire, southern Scotland, where near horizontal old red sandstone strata overlie steeply dipping Silurian gray wax. Don't know what the fuck that means, man. Don't know what a gray whack is. What the fuck is a gray whack? But I know sandstone is a type of stone, it's a type of rock, and it overlies steeply dipping Silurian gray wax. I'm guessing that Silurian gray wax is another type of rock, and steeply dipping means it goes like this. It's slanted. Beneath the unconformity, Hutton recognized the ruins of an earlier world, establishing the immensity of geological time. This paved the way for our present concept of the Earth as a dynamic and changing system, a forerunner to the current Gaia hypothesis, which describes the Earth as a living organism in equilibrium with its biosphere. Although the Earth is not actually a living organism, this concept now forms the basis for Earth system science. So it's almost behaving like an organism in the way that it changes, it almost breathes, how it erupts mountains, and the sediment goes down, and the crust is always moving. All right. Use of fossils. Discovery of biostratigraphy. Our understanding, all right, how long is this fucking video getting? We're at 31 minutes. Our understanding of the role of fossils in stratigraphy can be traced back to the work of William Smith in Britain and how do you pronounce that name? Georges. I want to say Georges, but I know it's French. I'm just gonna say fucking Georges, man. I don't want to say Georges. Jorge? Is it Jorge? I'm going to say Jorge. So William Smith in Britain and Jorge Cuvier and Alexandre Brongniart in France. William Smith, in the course of his work as a canal engineer in England, realized that different rocks units were characterized by distinctive groups or assemblages of fossils. In a traverse from Wales to London, Smith encountered successively younger groups of rocks, and he documented the change from the trilobite-dominated assemblages of the lower Paleozoic of Wales through upper Paleozoic sequences with corals and thick Mesozoic successions with ammonites. I'm guessing ammonites, corals, and trilobites are all different types of organisms. Finally, different types of life. Finally, he reached the molluscan faunas of the tertiary strata of the London Basin. And that's figure 2.1c. Can we see this? This is 2.2. So where's 2.1? It's up here. 2.1c. This is what he was looking at. So we got mountains, Stonebrash hills, clay vales, chalk hills, and he's discovering all of these different layers and fossils within them. Whew, this is fucking dense. God damn. All right. In France, a little later, the noted anatomist Jorge Cuvier, together with Alexandre Brongniart, don't know, a leading mollusk expert of the time, ordered and correlated tertiary strata in the Paris Basin using series of mainly terrestrial vertebrate faunas. Okay, so he was looking at fossils of vertebrates occurring in sequences separated by supposed biological catastrophes. Okay, so they're separated by like extinctions and shit. Great deaths throughout history. Yeah. These early studies set the scene for biostratigraphic correlation. in very broad terms, the marine Paleozoic is dominated by brachiopods, trilobites, and graptolites. Have no idea what those organisms are. Whereas the Mesozoic assemblages have ammonites, and I'm guessing the Mesozoic comes after the Paleozoic. It has ammonites, belemnites, marine reptiles, and dinosaurs as important components. And the Cenozoic is dominated by mammals. Okay, yeah. Mammals and molluscan groups such as the bivalves and gastropods. So you have, in the Paleozoic, probably the earliest of these periods, we have brachiopods, trilobites, and graptolites. I don't know what the fuck those organisms are. But then you have the Mesozoic, which introduces ammonites, belemnites, marine reptiles. We know what those are. Reptiles in the water, and dinosaurs. Everyone knows what those are as important components. And the Cenozoic is dominated by mammals and molluscan groups. We all know, well, maybe not all of us know, but mammals came to be kind of top dog of the animal kingdom after the dinosaurs went extinct, and we all evolved from a shrew or some sort of other kind of mammal. For some reason, the mammals were able to survive the meteor that is theorized to have hit the Earth, killing the dinosaurs. Whew, all right. This concept was later expanded by John Phillips, 800 to 1874, who formally defined the three great eras. Okay, so we've got the three great eras: Paleozoic, ancient life; Mesozoic, middle life; and Cenozoic, recent life, based on their contrasting fossils, each apparently separated by an extinction event. Interesting. Each apparently separated by an extinction event. Many more precise biotic changes can, however, be tracked at the species and subspecies levels through morphological changes along phylogenetic lineages. So, more precise species extinctions and subspecies extinctions, maybe, or evolutions are being tracked here, and that can predict what the biome was like throughout different times, maybe. Very accurate correlation is now possible using a wide variety of fossil organisms. Okay, biostratigraphy, the means of correlation. Biostratigraphy is the establishment of fossil-based successions and their use in stratigraphic. You know what? This might be the video. This might be the end here. We've been going for 37 minutes. I think this is a proper end. I understand this was a bit complex. I don't know if anybody's going to make it to the end of the video here. If you did, you're a fucking G. You're the fucking man, or you're the fucking woman, or you're the fucking they, non-binary person. You're a fucking dog for getting to the end of this shit. And we're probably going to pick this up at some point. We're on page 27, just about. We're on page 26, about halfway through. Almost halfway through. So we'll pick this up at some point. I don't know when, but I'm going to make a playlist. And so you can follow the playlist if you want. That's what we're going to do. My name is Luke, and this is Castles in the Air. That is all. Goodbye.